Topics. Calculating the accumulation of quantities, such as area or volume. When we talk about calculating the accumulation of quantities, we are moving into the realm of integral calculus. Think of it this way. If a derivative tells you how fast a cup is filling up at a specific moment, the rate, the integral tells you exactly how much water is in the cup after a certain amount of time, the total accumulation. Here is how we calculate accumulation across different dimensions. 1. Accumulating area, 2D. In basic geometry, we find the area of simple shapes like squares or circles using fixed formulas. 1. However, in calculus, we use definite integrals to find the area under a curve that isn't straight. 2 plus 1. We imagine the area is made up of an infinite number of incredibly thin rectangles. By adding the areas of all these rectangles together, we get the total accumulation of space between the function $f, x, and the x-axis. The formula $text area equals int underscore a caret b f x dx $. 2. Accumulating volume, 3D. To find the volume of an irregular solid, we use a process called integration by slicing. 3. We calculate the area of a single slice, a cross-section, and then stack or accumulate those slices along an axis. 4 plus 1. Disk method. If you rotate a 2D curve around an axis, you create a solid of revolution. 5. We accumulate the areas of circular disks to find the total volume. Shell method. We accumulate thin shells, like the layers of an onion, to find the volume of complex hollow objects. 6. The formula, disk method, $V equals pi int underscore a caret b f x squared dx $. 3. Real-world applications. Accumulation isn't just for shapes, it's used to calculate totals in various fields. Physics. Accumulating velocity over time gives you the total displacement, distance traveled. 7. Engineering. Accumulating force over a distance gives you the total work done. Medicine. Calculating the accumulation of a drug in the bloodstream over several hours. Here are two concrete examples of how we calculate the accumulation of area and volume using integral calculus. Example 1. Calculating area under a curve. Question. Find the total area accumulated under the curve of the function f, x, equals x2 between x equals 0 and x equals 3. 1. The setup: we use a definite integral to sum up the area from the starting point, a equals O, to the end point, b equals 3, area equals O3x2 dx. 2. The integration, finding the antiderivative. Using the power rule for integration, integral xn dx equals n plus 1 xn plus 1, we find the antiderivative of x2, 3x3, O3. 3. Evaluation. Now we subtract the value at the lower bound from the value at the upper bound. Fundamental theorem of calculus, area equals 333 minus 303, area equals 327 minus 0. Area equals 9 units. 2. Example 2. Calculating volume, the disk method. Question. Find the volume of the solid formed by rotating the function f, x, equals x around the x-axis from x equals 0 to x equals 4. 1. The setup: when we rotate a shape around an axis, the slices are circular disks with a radius equal to the function's height, r equals f, x. The area of each disk is pi r2. V equals pi integral O4, x, 2 dx. 2. Simplify the integral. Since x, 2 equals x, the integral becomes much simpler. V equals pi integral O4x dx. 3. The integration: apply the power rule to x. V equals pi, 2x2, O4. 4. Evaluation. V equals pi, 242 minus 202, V equals pi, 216, V equals 8 pi approximately equals 25.13 units. 3. Why this matters. In the area example, you just calculated the exact space under a parabolic curve, which is impossible using basic geometry formulas, like L times W. In the volume example, you essentially calculated the volume of a paraboloid, a 3D headlight-shaped object. This is how engineers determine the capacity of tanks or the amount of material needed for molded parts. Source: D. Ample Basic Mathematics.